All right, this week we're going to be looking into convolutional neural networks. Specifically, we're going to be examining how you could use a convolutional neural network to identify if a picture of an individual is on another set of pictures. So this is the type of tool that would enable you to, for example, if you see someone on a camera, identify if they are on a list of suspects that you are interested in looking at. Now, we'll be doing this in a reduced form way on Jupyter. In practice, these require GPUs and some very, very expensive hardware, but the basic implementations are very similar. So let's go ahead and do this. So first and foremost, in Jupyter, you're going to need to create a new folder for this lab. Otherwise, things will get very challenging. So you can just do new and then folder up here, and that'll create a new folder. For me, this was called untitled folder right here. I'm going to check this, and then up here, click on rename. I'm going to go ahead and rename this to CNN. And we can hop into this new folder. And then within this folder, I'll go ahead and create my normal Jupyter notebook. So I'm just going to name this CNN Jupyter. You can name that whatever you want, it will not matter. Okay, first and foremost, for convolutional neural networks, we will need to install some specialized software. And then we are also going to download some data from a large repository of images. So first, let's go ahead and install the software. I'm going to copy these two lines over for you. So these are the two things that you have to install. First and foremost is you will use Conda to install. So this is just an alternative approach to installing Python modules. So Conda install -y-c. We're going to be pulling this from a PyTorch repository, and then we're actually going to download PyTorch. And then additionally, we need to install Torch Vision. Running these two lines will take a little while the first time. So I'm going to go ahead and do this. All right, now we have PyTorch installed, so we can move forward with the analysis. First, we need to download the images. So these are going to be the faces that we'll be downloading, we'll be analyzing. So let's do import. There we go. So here's the URL that the dataset we'll be using is at. This is a dataset that is from the University of Massachusetts at Amherst. And you can download this directly from the University of Massachusetts at Amherst by visiting their website if you so desire. I'm going to put that on the screen here now. And this is called the Labeled Faces in the Wild dataset. So it's a very challenging dataset generally to work with because it's dealing with pictures of people that were taken in uncontrolled environments. So we're going to, what we've done here is we've said essentially to go to this website and then download this file and save it here. So we are now going to have a file called lfw.tgz on our local drive. What we need to do now is essentially unzip this file. So down here, I'm going to do a couple of things. First, I'm going to do a tar, untarring it. So tar xvf lfw.tgz. So this is essentially going to run a command line utility that will tell it to take this file and open it up. Just like you would unzip something on Windows, this is the equivalent of that in the Linux environment. So I'm going to go ahead and run this, and this will take just a moment. All right, and there we go. So now we can take it, let's see what we got. So I'm going to type in !ls -l lfw. So what this is saying is show me ls list all of the files in the directory lfw. So this will give me an idea of what we just unzipped. You could simply browse back in Jupyter and look at your home directory and then open up these files. But by going in that direction, because there are so many faces included in this particular data set, that would probably crash your Jupyter browser. And so this is a way we can look at that programmatically. So go ahead and run this. And here we go. So this is the set of files that we now have. So we have a whole bunch of folders, Aaron Eckhart, Aaron Julio, all the way down to Ahmed Masood. There are thousands and thousands of individuals that we have images from that are saved and named. So we're going to be using all of these to train an algorithm that effectively takes in any image and matches it to, well, could potentially match it to a twin. It would try to detect the image that it's the most similar to. First, let's take a look at just one of these so we can get an idea of what's going on. So ls -l lfw. Let's just look at Aaron Eckhart. Run this. And there we go. So this is inside of Aaron Eckhart's folder. We see that there is one image. So this is just one JPEG that we have of this Aaron Eckhart fellow. Now let's look at a slightly more famous person. So we have data on Fox, President Fox. And here we go. So we can see in this case we have 32 images that are all of the same individual. Fundamentally, the way that we're going to train our network is we are going to teach the network to be able to distinguish between a picture that is of the same person and a picture that is of a different person. So let's take a look when we say a picture, exactly what we're looking at. So let's just look at one of these pictures. There we go. So this is just one picture. So all of these pictures are reasonably similar. We can type in any of these. So I mean, we could take a look at 0, 0, 3, 2, just to show another one, right? So this is another picture of the same guy. So the goal here is to teach an algorithm that this and this are the same person. And so we're going to iteratively go through and basically tell the algorithm that those two pictures are the same, and then contrast that to a lot of cases where they are different. And you'll see, I mean, these pictures are highly varied depending on exactly who we're looking at. They're all in very different contexts. So this is, you know, someone sitting in front of a lamp, but you'll have other cases where they're in the middle of a judicial hearing, or all sorts of other contexts depending on who they are and what they're doing. Now we need to build twins. So we need to identify an image like this of Vicente Fox. We need to be able to put beside it a twinned image that is of the same person. That's the first part of what we're going to be using to train our network. To do this, we'll need to use something called the Python image library. So to get that installed, you'll need to type something like this in. And there we go. So we now have PIL is what it's called. The Python image library is installed. And so let's just import a few things we'll need. Okay, the code we're going to write now is going to be the baseline code that we'll be using to create these twinned images. So the first thing we need to do, and this is just going to be an example, we'll automate this later on, but the first thing we need to do is identify two faces, two images that we know are of the same individual. So I'm going to define face 1 and face 2. So these are going to be the two images we'll open, and then we actually want to add them onto a canvas that we can visualize. So we're going to do a very rapid cut of this first. All right, and there we have it. So let's walk through what we just did. First, we opened the two images. So this was completely arbitrary, image 1 and image 2. You could pick any two of the same individual. We then defined the total width of the new image we were going to create as the sum of the width of these two images. We defined the height of the new image we were going to create as the maximum height of these two images. Then we create a new image. So this is the new image that this is just a blank image at this point, a black background that has a width equal to the total width we defined here, and then the max height that we defined right here. Then into that black box, we're going to paste face 1. And face 1 in this case is the first image. So it's going to be the image that's on the left here. Face 2, we then paste the exact same way, but we paste it starting at the end of face 1. So when at the width, basically starting at the width equal to the size of face 1. So the second image will not be copied on top of the first image, rather it's going to be placed to the right of the first image. We then save this, and we show this image example.jpg just outputs it to our Jupyter so we can see what happened. Now, we could just use this. We could actually feed these twins into our neural network. However, we can do better. There's obviously a lot of noise here, right? The lamp in the background, the person talking in the background, that is not the person we are interested in. The lamp is obviously not the person we're interested in. There's a lot of noise here, so we want to try to reduce the noise. There's also a problem with image intensity. So as you can clearly see, the image on the left is much brighter than the image on the right. And so we want to go through some sort of a normalization. Essentially, the convolutional neural network will be able to pick up things like straight lines, clearly defined features in the image. And so we want to do a little bit of processing to make the computer's job easier in that regard. So the first thing we're going to do is we're going to just simply convert these two faces into grayscale. And there we go, just like that. We now have grayscale images. So we've just changed these two lines. The other thing we can do very quickly, just to give the computer a better chance, is to crop these images. So the person we're most interested in is in the very center of these images, and that's generally true for a lot of the database. So we can get rid of some of the outside information and try to focus in more on the individual face that we're most interested in. And there we go. So now what we've done here is we've taken the grayscale, because we've already applied the grayscale here, and now we are taking the input face, we are cropping it to 224 by 224 pixels, so we're making it a little bit smaller. We are allowing some bleed, so there's going to be some information on the very edge of the images that can be interpolated. And then centering, this tells it where to crop from. So we want to crop from the very center of the image because that's where these faces are. So that results in a smaller overall frame that we're actually focused on. Now, this may look a little bit blurrier, and it is absolutely a little bit blurrier because we've intentionally reduced the total amount of data in the images. However, the data that we're looking at now is generally going to be more relevant. There's going to be less noise in terms of defining what these actual faces look like. Now we want to do basically the same thing, but for all twins in our database. So there's going to be a lot of different individuals in our database that we have more than one picture of. And we want to loop through all of those and create all of those permutations of what twins are. Because the more twins we have in our database, the better the neural network will be able to learn. So let's go ahead and write a very, very simple routine that allows us to do that. First, we'll do a few imports that we'll need for this. And then one thing we are going to do one time only is we are going to go ahead and create a new directory, which we are going to call twins. This will be the directory that holds all of the copies of twinned images, because we will ultimately have thousands of examples of twins. Okay, so you'll see this exclamation mark, make dear twins. Again, this is just running a Linux command on terminal to create a new directory called twins. All right, from here, what we want to do is go ahead and write some code that will essentially loop through the code we already wrote. So this code that created this single example of a twin, we're going to do the same thing, but over and over and over again for all of the different permutations of twins in our database. So we're going to want to, for every single individual, create a set of images that looks like this, where it's kind of just comparing two different images of the same person, and that's what we're calling our twins. So let's go ahead and write this loop. Okay, so we're going to walk through this reasonably slowly. So the first thing you'll see we're doing here is we are iteratively going through every single folder in our directory, and we are identifying basically, first this is going to go through a for loop. It's going to look in the Mike Easley folder, then it's going to look in the Jerry Seinfeld folder, so on and so forth until it's recursively gone through every single folder. Within those folders, we then want to look at the files. So that's what the next part of this code will do. And just as an example here, so you can see this is the same thing. So we've now gone through each one of these folders, and all we're doing is we're printing out the names of the files within those folders. So it's going to iteratively go through every single one of these. You can see in some cases there are multiple images for one name, and in many cases there are not. So in this twins algorithm, there will be a lot of cases where there's simply, there's not a twin. There will not actually be a twin. So we need to put an exception in that says to skip this particular section of the loop in the case where there is no twin. So the first thing we're going to do is do a check to see if there are more than one file in the directory. And there we go. So right now this will only happen, we will only create twins if there's more than one image within a given folder, because every single time we're kind of recursively going through folders. Now let's take a look at this. When we do this, this should only print cases where there's more than one image. There we go. So now these are all the cases where we have at least one image that we can create a twin with. Now we want to do one other thing that is just because of the limits of our computation. So you can see in many of these cases there are many, many, many different images. So, on tennis superstars, we have a lot of pictures of. If we were to create every single permutation of these twins, it would be the total number of twins squared, because every single one of these has to be matched with every other one to create all of the twins that we possibly could. In some cases, for example, somewhere on this list is George W. Bush. There we go. We have literally hundreds of images of George W. Bush. And so that would take ages to create multiple twins for just one individual. We do want to limit this because that can also bias our model. If, for example, if we have hundreds of copies of George W. Bush, then our model will become heavily biased towards matching twins of George W. Bush. So we want to ensure some amount of equality. However, we also don't want to throw out too much data, and so we have to find some sort of a good medium. In this particular case, what we'll do is we'll just limit the number of files to 5 for every single case. So we'll go ahead and implement this now. And there we go. So this is the same thing, but now we can find George W. Bush. Let's see if I can bring him up. Search for Bush, perhaps. Laura Bush, and there we go, George W. Bush. So now you can see we only have 5 images of George W. Bush. So we've truncated that total size. So now we can move forward with our twins, where we'll only have 25 possible combinations of George W. Bush, rather than hundreds, if not thousands. Okay, so now let's actually move forward. The next thing we want to do is define our twins. So when we go through these different directories, we effectively want to say, okay, match George W. Bush 0268 with 0257. Now match 268 with 307, 268 with 184. We'll even match 268 with 268, so we'll end up getting that kind of double redundancy data because that is a perfect twin. And so we do want to teach the model what a perfect twin looks like. So to do that, we're going to do 2 different loops. First, we're going to say, okay, for every single file in this particular folder, let's go through each file, and then we're going to do it again. We're going to say, okay, for 0268, go through the list again. For 0257, go through the whole list again. For 0307, go through the whole list again. So we'll do it twice. To do that, we will simply need 2 for loops. So that looks like this. This is defining the images that we might create twins out of. So as an example, David Dodge, we have 2 images in his folder, 1 and 2. The first twin that we would create, well, in this case would be 2, and then 1 and 2, 2 and 1, so we get the inverse of these, and that is important for training the convolutional neural network, and then 1 and 1. So this is the 4 possible combinations of David Dodge, and we want to create those twinned images using every single one of these cases. So we want to create something that looks just like this, but we want to create 4 of those for just David Dodge. And then, of course, iteratively, we want to do that for everyone. So this part is a little bit easier. We're mostly just going to be copying the code that we created up here down into this file, this loop, but we're just going to be replacing. So here we have file I and file J. Here we defined those 2 files manually, right? So we just typed in .open, and then here was the file name, .open, and here was the file name. We're essentially going to do the same thing, but instead of manually typing in the file name, we're going to be using file I and file J. So let's go ahead. Okay, and here we have it. So here we have the for file I, for file J. This is what we already had, and then this is the new code that I just added in. So when I run this, what it will effectively do is every single time it will increment the number of twins by 1. So we'll be starting at 0 and then adding 1, 1, 1 every single time. We have our first face defined here, and this is the path to file I. So in the very first case, this will be /LFW/David Dodge/David Dodge 002. That's what this full thing will resolve to. Same thing here. In this case, the very first time, it will also be David Dodge 002. The second time this happens, it will be David 002 matched with David 001. This is identical to what we implemented before. We're going to go ahead and convert into grayscale. This is also identical. We're going to crop so that we're looking at just the center of that particular image. And then all of this is also identical. So we're just going to do that pasting into this format, this kind of 2-person format. The only thing that changes down here is where we're saving. So we're going to save into our twins folder, and we're going to save it as a JPG with the name of the current iteration. So this will increment every single time this for loop happens. So let's go ahead and run this, and this will take a while to run. We'll talk a little bit about how you can use Linux to observe how far you've gotten. So I went in and clicked run because this takes a while. While this happens, one thing you'll want to do is let's jump over into terminal, and I will show you how to see kind of the progress of this particular script. Later on in this video exercise, I'll teach you how to do this within Python. All right, so I've gone ahead and opened up a terminal, and I'm going to type in ls just to see where I am. In my case, I'm going to type in cd cnn because this is the folder that I'm currently running the lab in. So ls again. You'll see that twins folder. So I type in cd twins and type in ls. And this is a list of all of the twins that have currently been built. So we can now type in, well, first cd ... to go back, and now we can type in There we go. So you can see there's 4779 twins that have been created. I'm going to push the up key on my keyboard and hit enter. And you can see over time now we're at 5,759, 6,142, so on and so forth. So you can observe the progress of how many twins have been made in your script using terminal like this. One note is the icon that looks like this. So you'll see that that's called a pipe. That is if you hold down shift and your backslash key. That is how you get this pipe. So with that, pop back into Jupyter. Okay, let's take a look. So that is now done. There are around 19,300 twins. So I'm going to go ahead and just take a look at one of these. There we go. So this is just one example of a twinned image where we have two different pictures of Halle Berry in this particular case. We can look at any of our twins we so desire. There are going to be thousands of these. So this is another example of a twin, where essentially what we want to do is we need to be able to teach the algorithm what a twin is. What are two faces that look the same? And so that's what we are defining here. Now we need to do the opposite. We actually need to define two faces that look different. So in this case, we're going to do essentially the same thing we did here, but in this case, we're going to be looping through the other direction and we'll be creating difference images. Now, keep in mind there are about 19,300 twins. Specifically, there are 19,302. We can technically have as many difference images as we want, but the more that we have, the longer our neural network will take to train. In this case, we're going to intentionally pick 19,302 of our difference images, and that way we won't have a huge number of faces we have to train on. And in addition, we will kind of have a balanced network. That is the same number of cases of both pro, yes twin, and con, not twin. So let's go ahead and do that here. First, we need to create one time this directory called diff. And so this will just be just like we did up here where we have twins. Here we're going to have diff. So we'll have those two different folders. And now we'll kind of just write the same code. And we'll actually start essentially with the same thing here. I'm going to type it all out manually, but you'll see very, very, very similar types of logic as to how we created our twins. All right, we'll pause here for just a moment, and I'll try to walk through this code as slowly as possible. Here, what we're doing is we're saying go through all of our folders and pick a random folder. Then, in that folder, pick a random face. Then save the path to that face. So I'm going to run this, and we'll just take a quick look. Run that, and we'll take a quick look. And here we go. So you can see this is just picking a random face within every single one of these folders. So we're going to do that twice, once for face A and once for face B. And then once we've identified a set of faces that are different, they're from two different people, then we'll save those as our new not twin image. Okay, and here we go. So you'll see some very similar logic here. First of all, face B name. This is the second name. We do a quick comparison to see if A and B have the same name, and if they do, we just don't do anything, and we'll record how many times that happens. Fortunately, we have enough names that this is very, very unlikely to occur. Then we are going to go ahead and create our different face image. So this is going to be identical to what we've done above in terms of creating that image. The only difference here is that we are saving this into the folder called diff, D-I-F-F, which you'll remember we created just a moment ago. So here we're going to have a folder full of images that are different. And when this is successful, we just increment our counter so that we ultimately are trying to create 19,302 of these. Now this will also take a little while to run. So in this particular case, you can use the same trick we did last time of looking at terminal to see how long this will, or to see how much longer you have to wait. Now let's take a look at our different images. So just we'll pick one that is an example here. There we go. So this is just one example of two faces that are different. And we can take a look at any of these. We should have around, well, we should have exactly 19,302. So you can see just images that are clearly different people. So in our algorithm, we're going to train this. So these are zeros, our twins are ones, and we want the algorithm to identify things in this image. So for example, is there a straight line that has certain characteristics, vertical lines that have certain characteristics that are different from these images that are different from one another. So we'll be doing that, and we'll start using this data for training in the next set of videos.